century ago, Albert Einstein proposed the idea of so-called gravitational waves, which we'll come to later, which were part of his theory of general relativity. This concept of gravitational waves suggests that the force of gravity is not an actual force, but rather the distortion in a fabric of space-time. This was just an idea. Einstein had no way to prove it, but this is why we're here today, because now we actually have a way to prove it. Yeah, we all know Einstein was kind of crazy and brilliant. And so scientists decided to invest $1 billion, a bit more than $1 billion, into this project, which we know as Ligo. And maybe they're just thinking, land art, beautiful. Or they actually wanted to detect what gravitational waves are. And so we came up with the project Laser Interferometer Gravity Observatory. Everyone say that 10 times. That's like saying the German word Schwarzwälder Kirschtorte. So why exactly do we need LIGO? So first of all, LIGO confirms Einstein's theory of general relativity. There's another reason for it. It is a really, really great way of studying the universe because gravitational waves can help us understand the universe far beyond the apparent. And so we can look at phenomena such as like the collision of stars, what happens inside of stars while they're colliding, these kind of things that we cannot see through a telescope. And so it's a way of seeing without seeing. It's a way of seeing without like seeing the light, but rather the gravitational waves.
In 1916, while World War I raged on, Albert Einstein predicted something more powerful than any weapon in the war: gravitational waves. Now, usually when we think of waves, we think of water, but now we're dealing with space-time. And instead of surfers or rocks dropping, we're dealing with planets, black holes, and other massive objects in our universe. Going along with the idea that these objects can stretch and bend space-time, in Einstein's theory, he realized that massive accelerating objects could disrupt the nature of space-time in such a way as they send waves throughout space-time in all directions away from them. These ripples sent by massive objects move at the speed of light, sending information about their origins as well as clues to the nature about gravity itself. So what can cause a gravitational wave? Well, anything can. Cars, airplanes, even ourselves. But these things have masses that are far too small to create gravitational waves that can be detected by any instrument. Rather, more common sources of detectable gravitational waves are orbiting black holes and neutron stars, as well as massive stars blowing up at the end of their lives, called supernovas. If a massive object like a neutron star's spin rate stays constant, it will create something called a continuous gravitational wave that would be detected at the same frequency and amplitude. Gravitational waves have helped to put much of the theory of cosmology into real terms, and LIGO has provided us with clear results and evidence of such waves in our universe.
LIGO is able to detect these gravitational waves using laser interferometry, or the interference of light waves. Laser interferometry essentially measures the distortion in space-time caused by passing gravitational waves. The way it works is that a laser is sent to a mirror set at 45 degrees that allows half of the light to pass through and continue in a straight line, and deflects the other half of the light perpendicular to the original path. At the end of these two paths are mirrors in which the light will be deflected off the mirror back in the direction in which the light came from towards a detector. Now these two mirrors are equidistant from the detector, so assuming no gravitational waves are present, the light waves from each mirror should interact destructively and nothing will be detected. However, if gravitational waves are present, gravitational length contraction will cause the distance between the mirrors and the detectors to change. Thus, the light waves will interact constructively and will receive a signal indicating that gravitational waves are present.
According to Einstein's theory of general relativity, any massive object that is subjected to an acceleration will generate a gravitational wave. That means that this produced a gravitational wave fundamentally altering the shape of space and time themselves. However, Einstein also calculated that the amplitudes of such waves were so small that they would be nearly impossible to detect with human instrumentation. LIGO, which is the first instrument that is sensitive enough to detect a gravitational wave, entered operation nearly 100 years after Einstein published his theory of general relativity. It is an exceptionally sensitive device, capable of detecting distortions in space as small as 1/10,000th the diameter of a proton. Yet, even with this extraordinary sensitivity, LIGO is still only capable of detecting the largest gravitational waves, which are those produced by so-called cataclysmic cosmic events. The first successful identification of gravitational waves occurred on the 14th of September 2015 when LIGO's detectors identified the distortions in spacetime created by two black holes merging together and forming a larger, rotating black hole. These two black holes were estimated to have had around 30 times the Sun's mass apiece, and were located around 1.3 billion light-years from Earth, which means that although the waves created by the collision are just now reaching us, the collision itself actually occurred over 1 billion years ago. Since this groundbreaking, Nobel Prize-winning first detection, LIGO has identified the gravitational ripples produced by other large-scale cosmic collisions. Notably, it was LIGO that, in 2017, identified the gravitational waves produced by the first documented merger between two neutron stars. Another significant finding made by LIGO was the 2019 identification of an object with mass 2.6 times that of the Sun in the so-called mass gap between what is expected for neutron stars and black holes. This object is theorized to be either the largest known neutron star or the smallest known black hole. With a new suite of upgrades known as LIGO Voyager, potentially capable of doubling the instrument's sensitivity, set to be installed in the next few years, it is almost certain that this incredibly advanced scientific laboratory will continue to make important discoveries regarding the cosmology of our universe.